Hello everyone, I'm Carlos Fernandez Granda from the Granda Institute of Mathematical Sciences and the Center for Data Science at NYU, and today I'm going to talk about the power of random sampling. This is a lecture for the NYU AI School. The goal here is to understand random sampling using basic concepts in probability, such as random variables and independence. This will illustrate how useful probability theory is for data science and for machine learning. We're going to focus on a particular example, which is that we want to estimate the prevalence of COVID-19 in New York City. So a few weeks ago, these are rough numbers, there were approximately 50,000 tests in New York City and 2,500 of them were positive. Does that mean that the fraction of people, which is the prevalence of COVID-19, the fraction of people that had COVID-19 in New York City was 5%? Think about it for a moment. I really recommend that you think about it for a moment before continuing the video. Well, the answer is that we don't know, right? As an example, back in March, in March 2020, in particular on March 29, 70% of the tests in the city were positive. Does that mean that 70% of people in New York City back then had COVID-19? Definitely not. What was happening is that there weren't that many tests available, and the people that were being tested were essentially people that were showing up in the hospital with severe symptoms. So that's why the fraction of people out of those that were actually positive was so high. Does this 5%, is this 5% more representative? Well, we would have to know how these people that were tested were selected. And that's a very important lesson, very important point in machine learning and data science in general. If you have flawed data acquisition, or maybe perhaps I would even have should have said, if you don't understand your data acquisition, this can render even the best machine learning method, even the fanciest deep neural network, completely useless. Here we're going to see that random sampling actually ensures that your data are representative of reality, which is like a necessary condition for any machine learning method or any statistical procedure to actually work. And in fact, if we sample uniformly at random, which means that everyone is equally likely to be tested in the city, we can determine the prevalence of COVID-19 in New York City to a very high accuracy with relatively very few tests relative to the total population. To understand why this is the case, we need to learn or review, in the case of some of you, some probability theory. So the idea here is that we're going to use random variables to model the tests. So let's focus on a single test. In a single test, we're going to represent the outcome of this single test as a random variable x. A random variable is a mathematical construct that we use to represent quantities that are uncertain. We don't know they don't have a fixed value. They can have different possible values with, as we will see, different probabilities. I will talk about probabilities in a moment. So in this case, the test could be positive or negative. If it's positive, we're going to say that x is equal to 1. If it's negative, we're going to say that x is equal to 0. Notice that x can be equal to 1 or it can be equal to 0. Okay, so here we're modeling the test before we know its outcome. The random variable has the probability of being equal to 1, a probability of equal to 0. It's never going to be equal to 1 or 0. Okay, it can have these different values in a way at the same time. Okay, so again, a random variable is just this construct that allows us to model quantities that are uncertain. Okay, so as I said a moment ago, we use probabilities to describe random variables because they can have several values, so we need to somehow express how likely it is for them to take those values once we actually observe the outcome, in this case of the test. So in order to define probability, the intuitive meaning of probability is that if we observed the outcome associated to this random variable many times, an arbitrarily large number of times, the fraction of times that the random variable is equal to a particular value, for example 1, that is the probability. Okay. Of course, normally we deal with a quantity and we don't necessarily observe its outcome, and we definitely don't observe its outcome over and over and over. Okay, the probability just is associated to that thought experiment where you would do it over and over. Okay, we test someone in the city. Before looking at the outcome of the test, what's the probability that the test is positive? That represents the fraction of times that it would be positive if we repeated this many times. Okay, this is the idea. Same for x is equal to 0, or the test is negative. If we repeated this over and over and over, what's the fraction of times that the test would be negative? That's what's captured by the probability. In our case of interest, let's assume that the fraction of people in New York City that have COVID-19 is equal to P, where P could be, I don't know, 0.1, 0.2, whatever it is. In that case, if we pick someone completely at random and everyone is equally likely to be picked, what is the probability that the test is positive when we test this person that we picked at random from the whole population? Well, it's just the fraction, it's equal to the fraction of people that actually had COVID-19. So in this case, very conveniently, the probability that is x is equal to 1 is equal to p. Again, we're picking just one person, okay? What is the probability that the test is equal to 0? Sorry, that the test is negative, or equivalently that x is equal to 0. The probability is just 1 minus p, because that's the fraction of people that do not have COVID-19 under our assumptions. Okay, so now how are we going to estimate p, the prevalence that is really what we're after? Well, a reasonable thing to do is to just do a bunch of tests in the city, but making sure that we're picking people uniformly at random, so everyone is equally likely to be tested, and we compute the fraction of positives. Okay, so mathematically, we have this n tests, where n is whatever number of people we have decided to test. We sum up the random variables, because notice that each positive test is means that one of these random variables is equal to 1. So the fraction of positive tests is just adding them up and dividing by the total number of tests. And that's going to give us an estimate of the prevalence, an estimate of p, which is what we want to estimate. Here, though, we have to wait for a moment, because the way I've defined things, there's something that is quite unclear. So I'm going to put my mathematical hat on and say that, wait. So here we've just said that everyone is equally likely to be tested. But what if we picked a person at random from the whole population and we tested this person over and over again, so that these n tests are going to have the same outcome because they're associated to the same person? This is obviously useless, right? Because when we do this average that I was talking about before, this average is going to be equal to 1 or 0 depending on whether that person has COVID or not. So it's really not going to tell us anything about the prevalence of COVID-19 in New York City. This is a really terrible thing to do, but this terrible thing to do actually satisfies the way I've defined things, because I've just said that each of these random variables is equal to 1 with probability p. And this, if you think about it for a bit, in this situation that actually holds. The problem is the dependence between them. The problem that is that these tests are dependent in this made up situation that I just described. So we need to also describe the joint behavior of these random variables if we're going to analyze what's going to happen. Like, we're going to analyze effectively this way of estimating the prevalence. Behavior of two random variables can be described using their joint probability, which is defined in a very similar way to when we define the probability that an individual random variable is equal to a particular value. So given two random variables x1 and x2, their joint probability quantifies how likely it is for them to be equal to certain values at the same time. So for example, if x1 and x2 represent these tests, and they're equal to 1 if the test is positive and to 0 if the test is negative, the probability that x1 is equal to 1 and at the same time x2 is equal to 1 is again defined very similar to before. The thought experiment here is we would carry out these two tests over and over and over and over. Each time, okay, each repetition would be, in each repetition we would carry out both of the tests. Then out of the total number of repetitions, we would count in how many of them both of the tests are positive. Or if we're interested in the probability that x1 is 0 and x2 is simultaneously 0, we would count how many times both are negative, and similarly for the probability that x1 is equal to 1 and x2 is equal to 0, or vice versa. Okay, so the idea is very, very simple. This the joint probability of the two random variables describes their joint behavior, which means what values they can take and with how likely it is that they take certain values at the same time. Another concept that is very important is the conditional probability. So again, imagine that we have two random variables, x1 and x2, that in this case represent tests that we're carrying out. The conditional probability of x2 given x1 describes x2 when the value of x1, the outcome associated to x1, has been revealed. Okay, so what is the probability of x2 being equal to 1 conditioned on x1 being equal to 1? Well, we define it in the following way. We again generate or observe x1 and x2 many times together. So each time we view the two outcomes, the outcome of associated to x1 and the outcome associated to x2. And now, out of those times, we only focus on the ones for which x1 is equal to 1, okay, because we're conditioning on that. And out of those, we see in how many cases x2 is also equal to 1. Okay, this is why here we have x1 and x2 are positive. Sorry, test 1 and test 2 are positive. You can view this as, like if you have all your tests here, you only pick the ones for which x1 is equal to 1, okay, and maybe like I can use another color, say that these are the ones for which x2 is equal to 1. What you're doing is basically taking this part here, okay. This part here is the number of tests for which x2 is equal to 1 and also x1 is equal to 1, and you're dividing it by the number of tests for which x1 is equal to 1. Okay, so this tells you when x1 is equal to 1, how likely is it for x2 to also equal 1. The idea is very similar if you're conditioning on x1 being equal to 0. In this case, you're only going to take into account the test for which x1 is equal the test 1 is negative, and out of those you're going to see for how many of those test 2 is positive. Again, this is just a thought experiment. We define the conditional probability to describe a situation where we're just carrying out two tests, and now we say, okay, but imagine the first test was positive, what would be the probability that the second test would also be positive? Okay, that's what the conditional probability captures. It turns out that there's a very simple identity that connects the joint probability and the conditional probability, which is called the chain rule, and we can derive it through this intuitive definition that we have done. So remember that the joint probability that x1 is equal to 1 and x2 is equal to 1 is just, if you repeated these tests over and over again, it will be the fraction of times that test 1 and 2 are positive out of the total repetitions. Now we can basically multiply and divide by the same quantity, in particular the number of times that the test 1 is positive, and by basic mathematics this preserves this equality, okay? So all of this is still equal to the joint probability of x1 being equal to 1 and x2 being equal to 1. But now, if we look at this, here on the left we have the fraction of times that test 1 is positive. That's just the probability that x1 is equal to 1. And here on the right we have the fraction of times that the test 2 is positive out of the times that test 1 is positive, and that's just the conditional probability. So it turns out that you can write the joint probability of x1 being equal to 1 and x2 being equal to 1 as the product of the probability of x1 being equal to 1 times the conditional of x2 being equal to 1 given that x1 is equal to 1. And these are this is a fundamental identity that you use all over the place in statistical modeling and machine learning. So now that we have all of these definitions in place, we can define a concept that is crucial to what we're talking about, which is independence. The idea of independence is that the value of a certain random variable does not affect the value of another random variable. In that case, these two random variables are independent. That sounds intuitive enough. Mathematically, what we mean by this is that if we consider the conditional probability of the second random variable being equal to any particular value, conditioned on the first one taking some value, basically that probability is always the same, and it equals to the probability that this second random variable, x2, is equal to, in this case, b. Okay, I realized that that was really confusing. Basically, the conditional probability of x2 being equal to b is always equal to the same value, which is the probability that x2 is equal to b, without taking into account the value of x1. Okay, I hope that was slightly clearer. And by the chain rule, which we proved we provided an intuitive proof a couple of slides ago, we have that when two random variables are independent, this just follows from the chain rule, their joint probability is equal to the probability of the first one being equal to a particular value times the conditional. Now here, if the two random variables are independent, the conditional is just equal to the probability that x2 is equal to b. So in the case of independent random variables, the joint probability just factorizes into a product of the individual probabilities. Okay, and that's what we're going to use now to analyze random sampling. So as I said before, dependence of tests when we're trying to determine the prevalence of COVID-19 in New York City seems like a bad idea, because we're not going to get as much information about the general population. So now our new plan is going to be to do independent tests at random. So we're still picking everyone so that everyone is equally likely to be picked. But now each time we pick, we make sure that our choices are independent. It doesn't matter who you picked before, you're going to pick again completely independently at random. Notice that you could pick the same person, but the probability that you pick the same person is so low that it's not going to matter. Okay, so now our new plan is we do a bunch of independent tests that are represented by these independent random variables x1 to xn, and again we're going to take the fraction of tests that is equal to 1, which is just given by the sum of these random variables divided by the total number of tests that we're doing. Now we're going to call the number of positive tests y, and we're going to divide that by n to get our estimate. So in order to understand how effective this approach is, we have to determine the behavior of this random variable y, which is the number of positive tests that you have out of a total of n. Okay? We want to determine the probability that y is equal to k, and realize here that k, the possible number of positive tests, goes from 0 to n. The idea is that when n is relatively large, the probability that y is equal to a value of k that gives you a good estimate of the prevalence here is going to be quite high. That's what we're going to derive. This hopefully will become clearer later. But for now, let's focus on what is the probability that you have k positive tests out of n. In order to compute that probability, you have to be a bit careful. You have to realize that the positive tests can occur in different orderings. So for example, you have a total of 3 tests, and 2 of them are positive, you can have 3 different orderings. The first 2 can be positive, the first one and the third one can be positive, or the last 2 can be positive. Okay? In general, what is the number of possible orderings when you have k positive tests out of a total of n? If you have ever seen simple combinatorics, that is given by this number, which is n choose k. Okay, we don't have time to go into detail here, but you can just look it up in Wikipedia or Google and you'll see an explanation. But that's the total number of possible orderings of k positive tests when the total number is n. Okay, so now let's go back to computing the probability. Let's compute the probability that you have k positive tests in a fixed order. In particular, to make things easy, let's imagine that the first k tests are positive and the remaining ones are negative. The remaining n minus k are negative. So we want the probability that x1 is equal to 1, x2 is equal to 1, up to xk is equal to 1. and then xk plus 1 is equal to 0, up to xn is equal to 0. We have made the assumption that these tests are independent. So by the chain rule and these properties of independence and conditional probabilities, we know that the joint probability is going to factorize into a product of the individual probabilities. And now these individual probabilities, because we're choosing people at random from the whole population of New York City, these probabilities are equal to p if the test is positive, and 1 minus p if the test is negative. How many p's do we have here? We have k. We're doing p times p times p, k times. How many 1 minus p do we have here? N minus k. Okay? So the probability that you observe this particular fixed ordering is equal to p to the k times 1 minus p to the n minus k. But of course we have to take into account all possible orderings. And if you realize this argument that we made would work no matter what this order would be, as long as you have k positive tests and n minus k negative tests. Why? Because here you're still going to get k probabilities that are equal to p in some kind of order, and you're still going to get n minus k probabilities that are equal to 1 minus p in some other order, but the order doesn't matter because you're just multiplying everything. So you're still going to get this same value no matter what the ordering. So now you can add all of these orderings to get the probability that you observe k positive tests if the prevalence is equal to p, and you're making a total of n tests. So actually our work here is done. This is the probability that if we do this random sampling procedure, we're going to observe k positive tests out of our n total. And now we can use this formula for different values of p and n to see what value of n would be acceptable. So let's imagine, for example, that we want to have an error of less than 1%. You can take a look at what happens when we have that n is equal to 100 and p, for example, is equal to 0.05. Here on this graph, the x-axis is k over n, so that would be our estimate. And we hope that our estimate is as close as possible to 5%. Okay. Each of these little blue dots tells you the probability that you end up with k over n being equal to 0.01, 0.02, 0.03, 0.04, that you're exactly right, 0.05, 0.06, and so on. Okay, so the good news is that the highest values are around the value that we want to estimate, okay, which is 0.05. The bad news is that other values are still relatively high. So to quantify this, we can compute what's the probability that if we do this, p is equal to 0.05 and we have 100 tests, what's the probability that we're wrong by more than 1%? And that probability is basically 1/2. So 100 tests is not an acceptable number. It's a ridiculously small number, by the way. I mean, again, there's 8 million people in New York City. So we want to be, if we want to have an error that is lower than 0.01, we better do more tests. So this is what the distribution looks like for 1,000 tests. Okay, again, if the true prevalence is 0.05, we see that it's much more peaked around this true value that is 0.05. We have a much higher probability of actually being right. Okay, like the values around 0.05 are quite concentrated. In this case, the probability that we make a mistake of more than 0.01, which is basically the sum of the probability of these other values, that is, 13%. So still, 13% of the time, if we do this procedure, we're going to be wrong by more than 0.01, which may not be acceptable if we want a very precise estimate of the prevalence. If we take 10,000 tests, which is still a very small number compared to the whole population of New York City, and it's definitely smaller than the number of tests that are being carried out right now every day, it turns out that the estimate that we're going to make, again, if we are estimating independently and uniformly at random, is extremely peaked around 0.05. In fact, we're for sure going to nail the prevalence to an accuracy of of more than 1%. Okay, like our accuracy, our error is going to be for sure smaller than 0.01. The probability that this doesn't happen is ridiculously small. So this means that with 10,000 tests, we're going to know the prevalence of COVID-19 in New York City almost exactly. I mean, well, not almost exactly, okay, like with an error of less than 1%. And in fact, significantly lower. Here I just fixed 1% arbitrarily. And given that the population of New York City is 8 million, this is actually quite spectacular, and it illustrates the power of sampling uniformly at random. You get data that are really representative of the underlying reality. Of course, sampling completely independently at random is not always practical. Okay, so just a quick recap. Here we have hopefully understood that data acquisition is completely crucial. Understanding the mechanism whereby you're acquiring data is a fundamental part of data science and machine learning. We have used random variables to model random data. We have introduced joint and conditional probabilities to describe the dependence between the data. And we have used all of this to show that independent random sampling works extremely well. And in fact, it's used all over the place, not only to determine prevalence of diseases, but also when you do polls and things like that to determine the outcome of elections, and essentially all over the place. Hopefully, this has driven home this message that probability theory is a key tool to design and analyze machine learning techniques. Thank you very much for your attention.